Once we've established some basic properties of limits, we want to do a little more to see what we can actually do with them. And the first of these are these limit laws, which give us ways that we can combine simpler limits into more complicated ones once we know these properties actually hold true. So in order to actually prove these and establish these, you have to use the actual formal definition from section 2.3, but we can get a pretty good intuitive idea of why they should be true from our more informal definitions. The limit laws basically say that assuming that I have two functions f and g, a point c, and then values L and M for which these limits exist, I'll highlight that one to make sure we establish that. The initial assumption is that these two limits exist and equal L and M respectively. Then what can we do? Well, then the limit laws say we can add limits, subtract limits, multiply by constants, multiply them together, divide them provided the bottom's not 0, take them to powers, and take roots of them. So all of these operations respect this idea of limits. Let's talk about a couple of them real quick. Let's talk about the sum one first. So what's the intuitive idea behind this sum rule? Well, the sum rule basically says that if I take the limit as x goes to c of f plus g, what I get is L plus m. And so the intuitive idea here for this is that I want to show that as x gets really, really close to c, f plus g gets really close to L plus m. So we would want to make f of x plus g of x minus L plus m arbitrarily small when x is close to c. But I can split that into two parts. By the triangle inequality, I know that if I look at f of x plus g of x minus L plus m, I can rewrite that as f of x minus L plus g of x minus m. And what do I know? Well, I know that because the limit of f is L and the limit of g is m, this is small and this is small. And the sum of two very small things is still small. So my result here is still small. Right? There's an actual proof behind this when you have the formal definition, but the intuitive idea is that basically, if I add two really small things together, I get a really small thing. So if I can make the two parts really close, the sum is also close. In a similar way, the difference is close, the product is close. The idea here is the same. They just get a little more tricky based on the different setups. So in terms of sort of actually proving this, the tricky parts are the product one, quotient one, and the root one. The rest are all not too bad. Sort of see intuitively why that might make sense. But what we need to do for this class is just know how to apply and use these different concepts. Now, why does the assumption matter here? Well, the assumption matters because if limits don't exist, you can break these things. Quick example of that. I can write 1 as x times 1 over x. Cool, great. So if I look at the limit as x goes to 0 of 1, this should match the limit as x goes to 0 of x times 1 over x, which by our rules from above should be the limit x goes to 0 of x times the limit x goes to 0 of 1 over x. And clearly the far left side here is 1. Limit as x goes to 0 of x is 0, and then we have this limit x goes to 0 of 1 over x. But 0 times anything is still just 0, so this tells me that 1 equals 0. Well, that seems not great. I just used, our new thing we just proved to show that 1 equals 0. What went wrong? Well, the issue was that this limit here doesn't exist. So limit x goes to 0 of 1 over x does not exist. And so I can't use our limit laws to split up and recombine these limits. So whenever you want to apply these principles, you want to add stuff, subtract stuff, recombine things, and multiplying, you have to make sure limits exist first, and then you can go through with the process. If the limits don't exist, it's going to break and it's not going to work. You can do this after the fact, right? You can do the process, and then when you verify that every piece exists, then justify, oh, hey, I could have done this the whole time because they combine my together and it all works. But you do have to at some point verify that all the limits involved exist if you want to apply these limit laws. Otherwise, you get 1 equals 0 and you break all of math. So please don't do that. So once we have these limit laws, what do they do for us? Well, we will establish in class, you can sort of think intuitively, the fact that for any value c, the limit as x approaches c of the function x is just c. The idea being if x gets really close to c, then x gets really close to c. And limit x goes to c of a constant k is that same constant. The gap here is always 0 no matter what you plug in, and so it's always arbitrarily small because it's always 0. So what do those statements there tell us about certain functions? Well, these statements here tell us that, in particular, for the function f of x equals x, the same function as we have written right up here, the limit as x goes to c of f of x equals f of c for any c. F of c is just c, and so this is the exact same statement as above. And the same is true for any constant function, because the constant function at c is also just k, and so that holds here as well. And now because we can add, subtract, multiply, and raise to powers, we get from that is we have x, we have constants, and we have those rules of adding, subtracting, multiplying, and raising to powers. I can build all polynomials. So what that tells me then is that for any polynomial, p of x, it is true that the limit as x goes to c of p of x is just p of c, again, for any c, because I've built it from the limit laws and our two basic facts above. We can go one step further and go to rational functions. For any rational function, r of x is p of x over q of x. We have limit x goes to c of r of x equals r of c, or written slightly differently, limit x goes to c p of x over q of x equals p of c over q of c for any c, except what? Well, limit laws say we can only divide things when the bottom is non-zero. So for any c except where q of c equals 0. As long as we avoid dividing by 0, these laws work, and I can just evaluate this way. This leads us to a potential rule for evaluation of limits, and that is what's called the substitution rule. And this says that if f is a polynomial or f is a rational function with c chosen so that the denominator is non-zero, then limit x approaches c of f of x is just f of c. And the key point here is for these particular kinds of functions, we can evaluate limits just by plugging in the desired point. Now, these obviously are not the kinds of functions where it will be not defined at that point like our earlier examples, and so in those cases we need another trick to make that work. But in these particular cases, when we have a polynomial or a rational function at the bottom being non-zero, we were able to just plug in the limiting value, plug in the c, and that will give us the value of the limit. These things always match for polynomials and rational functions of this form, and so in these particular cases we can just use that. We will expand this idea a bit in a future section, section 2.5, but as of now, this idea only applies to polynomial and rational functions. So there are the limit laws. That's what they can build up to, giving us things to do with polynomials and rational functions, and we can use them in many different ways to build up a lot more complicated things that we will see over the next couple of weeks.